Hey everybody, and welcome back to Algebra 2 Online. So the plan for today is to just do a little bit of kind of review with some of the concepts we've had over the last few videos here. And one of the kind of more important ones, I think, that you end up seeing definitely a lot more in pre-calc and calc, but problems like this. Basically giving you certain information about the end behavior or over here, some of the internal behavior of a rational function and using that to get an equation of it. So what I would do for this is I would think about a picture. So you've got, you're told that basically out at infinity and negative infinity, the limit of the graph is approaching 3. So 1, 2, 3. So we know that it's sort of approaching that as a horizontal asymptote. Then it's saying that over at 4, 1, 2, 3, 4, you're told that from the right side, right, as you approach 4 from the right, the function value is going way down. And then as you approach 4 from the left, the function value is shooting up. And so that means that there's some sort of vertical asymptote at this spot. And so we're getting this kind of behavior where, again, based on this bullet point, as we come into 4 from the right, we know that we're shooting down, and so we're looking kind of like that. And then based on this bullet point, we're doing that on the other side. And so now you can write down the equation of a rational function that does this if you just kind of use like function transformations and things like that. So what I'm basically doing is I'm basing it off of our normal kind of parent function, like our normal odd parent function 1 over x. And so based on that, I can see that it's flipped, right? So there's like a negative. I can see that it's shifted to the right 4, so I'm going to need a minus 4. And then it's also shifted up 3, so I'm going to need a plus 3. So this equation, if you graph it in like Desmos or something, you're going to see something that basically looks like that. It fits these 4 conditions right here. All right, so this one is just asking you to write another equation, but a little more involved here with what we're basically given. So here it says it has vertical asymptotes at 2 and 3, okay, which you can see there and there. A horizontal asymptote at y equals -1, right there. And remember, again, you can cross horizontal asymptotes. You cannot cross vertical, though. And we can't see this in the picture, but it has a removable discontinuity at x equals 0. So basically, that means that there's a hole right there at x equals 0. So one of the things, I think I'm just going to start with like this. So if... I just meant to underline and I did a horrible job. If you've got vertical asymptotes at 2 and 3, then you've got factors on the bottom like x minus 2 or x minus 3, right? Because those are, if you plug in 2 or 3 there, then you're going to get a undefined situation. You're going to get those vertical asymptotes. So for the, probably the next thing maybe actually that I would do is the removable discontinuity at 0. So for this one, you just need basically a factor on top and bottom where you could get like 0 over 0, right? And so what you could do is you could put an x here and an x here, and since those would cancel out, those factor out basically, and then you at the spot x equals 0, right? You're getting that 0 over 0 thing. That is exactly what it means to have a removable discontinuity. So then the only other thing I'm missing is a horizontal asymptote at y equals -1. And for those, we know that we just need to take like if I had, 4x cubed minus x squared over 7x cubed or something, to find the horizontal asymptotes of a rational function, you just divide out by the biggest power. So I would divide out by x cubed here. And, whoops, did that wrong. That'd be 1 over x, and then this would be 7. And then you just take the limit as x goes out to infinity, right? And this one would go to 0, and so you would end up with 4 over 7. And that would be your horizontal asymptote. So what I need to do here is I need to identify the largest power that I've got, and then I would need to divide out by it and make sure that what's left over is just -1. And so on the bottom, in order to do these other things, I've got x cubed so far, right? So I basically need x cubed here. Otherwise, right now the horizontal asymptote would be 0, right? Because I would divide out by x cubed, and this would go to 0, and this would go to 1, and so the horizontal asymptote would go to 0. So I need this to be a power of 3, right? So if that's x cubed, then when I divide out by x cubed, I'll get 1, but I wanted a -1, so I just stick a negative there, right? And that will literally do it. If you do, y equals this thing, you literally get that exact equation right there. So that's kind of how you can build these things up from kind of pieces of information like this. So one other thing that I just sort of wanted to talk about with rational functions is inverses. So much of Algebra 2, we just spend the time basically learning about these elementary functions and their inverses. And we've learned a lot of these. We've learned that lines are inverses to lines, right? We've learned that quadratics are inverses to square root functions, sort of, right? We learned a lot about how they're not perfect inverse functions. And then we've learned about cubics, like x cubes, and how we can use cube root for that. They are much better inverses, right? Quartics are just x to the fourths, and so fourth root would work for those, right? So basically we've learned all about the polynomials and the corresponding root functions. And what I want to show you right now is what would be inverse to a rational function, okay? And I'll talk about this in a second too, but I'm going to jump over here, and I'm just going to compute the inverse. So standard kind of trick, just switch all the x's and y's. So instead of y equals there, I have x equals -2y over 2y plus 1 plus 1. And then now I just solve for y. So -1, x minus 1 equals -2y over 2y plus 1. Probably multiply by the denominator, so I get 2y plus 1 times x minus 1, -2y. If I multiply everything on the left there out, I would get 2xy plus x minus 2y plus, minus 1. And then this is pretty nice because I have a minus 2y on both sides, so that would cancel off, right? And then I could write that as 2xy plus x minus 1 equals 0. And so I'm trying to get y by itself, so we should probably move those terms that don't have y in them over. So I'm going to get 1 minus x on the right side. Then I can just divide by 2x, and I would do it, right? Y equals 1 minus x over 2x. So that would be the inverse function given this function. And more importantly, though, I want you to see that it is a rational function. So rational functions and rational functions are actually inverses. So it's one of those kind of like lines where their inverses are the same kind of type of function as the original one. This last point, so our next unit that we're going to get into are it's exponential functions, and you learned about these. These are the things that grow really quick like this, right? So what you haven't learned about are the inverses, and so we're going to spend a lot of time talking about the inverses. But it turns out that the inverses are something called a logarithm. So it's an A. We a lot of times abbreviate just log function, okay? Just like sine is abbreviation. It's really the way we write it in math is SIN, but really it's SINE. Not much of an abbreviation, but it is. So this is just going to be another really important pair of functions that you're going to learn about. Exponentials and logs act kind of reverse from each other, the way like quadratics and square roots, cubics and cube roots, quartics and fourth roots, and things like that. And that's not it even. And then there's going to be even more functions you're going to learn about this year. But this is going to be a very big unit. It's going to take quite a while. A lot of really important stuff in there with the exponentials and logs.